So one key thing to remember about standard reduction potentials is that they are only true for standard conditions. You can use them to get a rough idea of whether a reaction prefers to be an oxidation or a reduction, and comparing two different parts, right? If you wanted to make a galvanic cell, you could pick two of these half reactions, take the difference, and find the voltage from there. But those standard potentials are only true under standard conditions, right? So where all the activities are equal to 1. If we want to find the potential under non-standard conditions, which is like almost always, we generally don't have things at activities equal to 1. How can we find the potential for any arbitrary set of reaction conditions? And the way we do this is with the Nernst equation. So the Nernst equation is, we'll just write it out first and then we'll explain it. E equals E naught minus RT over NF natural log the activity of B raised to the B power divided by the activity of A raised to the A power. Let me specify that this is for some generic half reaction where we have A moles of A reacting with N electrons in equilibrium with B moles of B. Right, so this is just a generic reduction half reaction. Okay, and so we see there's this relationship where the concentrations, or more accurately, the activities of A and B are going to affect what the potential is compared to the standard potential, right? So everything is, again, this E naught here, this is the standard reduction potential. This is what you would look up in the table. This is a collection of constants, R, T, and F, right? So this is the gas constant, temperature in Kelvin, N comes from our reaction over here. So it's the number of moles of electrons involved, and F is the Faraday constant. And then what we have here is, this is Q, the reaction quotient. And so what this is saying is that the concentrations, or again, more accurately, the activities of A and B will affect. All right, so if A and B are activities of 1, then this whole second term goes to 0, and the potential will be the standard potential. But under normal conditions, that's not the case. Now, what's often done with this equation is if we say we're at 25 degrees Celsius, then we know the temperature, and if we combine a bunch of constants, and this is often written in terms of log base 10 instead of natural log, we can rewrite this equation as E equals E naught minus 0.05916 volts divided by N times log, now base 10 instead of natural logarithm, but still the same reaction quotient here. And in general, we're going to ignore the fact that these are activities and use concentrations instead in this class. But just to recognize that that is a slight approximation we're making, so that it won't give us complete. If we want to be more accurate, we can do this in terms of activities instead of concentrations. But in general, we're just going to use concentrations. So in the next video, we'll look at actually applying this equation and how we can use it to look at non-standard conditions and find potentials for those.